Hello, my name is Tristan.
And my name is Emmanuel.
And my name is Chandler Thomas.
My name is JT McClellan, and as a group, we're going to be showing off our producer consumer problem code, starting with Tristan.
All right. So before we even go over the code, let's first take a quick overview of our module. So the primary objective of our project is to develop a Linux kernel module tailored to address the producer-consumer problem, which is a quintessential illustration of synchronization hurdles encountered in an operating system design. At its core, the problem revolves around coordinating the interactions between two entities: producers, which are responsible for generating data or tasks, and consumers, which are tasked with processing or consuming these resources. The challenge lies in ensuring seamless communication and resource management between these entities, all while maintaining data integrity and avoiding conflicts such as race conditions. So key components of our solution will include a utilization of kernel threads and synchronization mechanisms. So we'll leverage these kernel threads as a backbone of our solution, facilitating concurrent execution of producers and consumers within the kernel space. And then to orchestrate seamless coordination between producers and consumers, we employ synchronization techniques, most notably semaphores.
And for semaphores, we have three of them. We have, could you scroll down just a bit? We
Yeah,
have the mutex semaphore, which is meant to be a lock on the buffer. We have the full semaphore, which is meant to keep track of how many spots in the buffer are full. And we have the empty semaphore that is meant to keep track of how many spots in the buffer are empty. And to get some of these values, we pass those parameters through the command line to our module. And those values that we pass through are buff size, which is the size of the buffer, producers, the number of producer threads we must have, and cons, which is the number of consumers threads, UUID, which is the user ID. And then moving on to the producer thread logic.
Is it my turn to talk about the producer thread?
yes, sir.
All right, thank you for scrolling on it. So in my segment, we delve into the pivotal role of the producer threads in our kernel module. These threads are tasked with identifying system processes owned by a specific user, designated by the UUID. This identification process leverages the for each process macro that we have in place, which filters the process to focus exclusively on those relevant to our user of interest as demonstrated below. This is our for each process task if task cred uid.val portion. And then moving on, upon finding a match, the thread then proceeds to securely record the process's details into a shared buffer. This step is critical, requiring precise synchronization to prevent any data mishandling. We manage this through semaphore operations, waiting for an available slot, which is our down interruptible at empty, ensuring exclusive access with the down interruption at mutex, and then signaling the addition of new data with the up at full. Here's a concise representation with the if down interruptible at empty, break, and so forth. Moving on, we employ a circular buffer strategy for efficient space utilization, incrementing the fill index accordingly. Moreover, to maintain transparency and aid in troubleshooting, each action is meticulously logged. In essence, producer threads play a crucial role in gathering and queuing process information safely and systematically, underpinning the module's functionality with robust data management and synchronization techniques. And I will pass on the torch off to JT to finish with the consumer threads.
Hello, my name is JT, and for consumer thread logic, these components, at least for the consumer threads, are tasked with processing the information collected by the producer threads, which we were recently just talking about. They calculate the total runtime as shown here and here. The process of interest efficiently managing the consumption of data with the shared buffer. This involves waiting for the buffer to be populated, which is the down interrupt at full right here, and ensuring exclusive access through the down interrupt at the mutex right there. And then finally processing the data, marking the buffer slot as available again through the up empty. Now, how it operates is that the whole loop right here continues until the stop signal is received, basically saying it's able to dynamically handle the process in real time. In conclusion, between the producer, consumer, and all these other threads within the kernel space, underscores the importance of synchronization and efficient data handling. Recently, I learned in 445 that it also prevents deadlock, which is another part of the race condition where two things are trying to access the same thing at the same time. So all in all, I wanted to thank you for letting us do this project, and have a good one.
Thank you.